Let's continue 3.4, zeros of polynomial functions. And let's see here. Our work in that previous example involved finding the zeros of a third degree polynomial function. The rational zero theorem is a tool that allows us to rewrite such functions as the product of two factors, one linear factor and the other quadratic. Zeros of the quadratic factor are found by factoring, or maybe the quadratic formula, or the square root property. Complete the square, so to speak. Okay, let's see what's going on here. In example 4, they want us to find all the zeros of this polynomial. The factors of our leading coefficient are positive and negative 1, and the factors of our constant here at the end, it's a nice prime number, so our only factors are plus and minus 1 and plus and minus 3. Because we're dividing by plus or minus 1, these are our possible real zeros of this polynomial. So we can do a little synthetic division test. We only have four of them, positive 1, negative 1, positive 3, negative 3. So we can just do synthetic until we find one of our zeros. Bring down the 1, and then we multiply and add, and multiply and add. That's supposed to be a 19. Multiply and add. We did not get a 0 remainder, so that didn't work. Again, bring down the leading 1, multiply and add. Multiply and add them up, and then multiply again, and we have a non-zero remainder, not a factor. Multiply and add, and a big remainder. So maybe fourth time is the charm. We got a negative 3 there for negative 12. Takes us to negative, there we go, jackpot, remainder of 0. So we know that negative 3 is one of our zeros. All right, and what we did is also knock this down to power. We started with x to the third. We factored out one of the factors, so what we're left with here is a 1x squared plus 4x minus 1. Okay, oops. I kind of got my squared. There we go. Okay, does this factor nicely? The factors a negative 1 that add up to 4. It's not going to work, not at all. So we are still, let me clear myself a little more room here. Don't lose sight of the fact we are looking for these zeros. So if I set this equal to 0, I want to get the answers out of there by any means necessary. And it looks like it's going to be quadratic or complete the square. My personal preference, since the number here in front of the x is an even number, I would go with complete the square. I'm going to move the negative 1 to the other side. It will become a positive 1. I set up my empty binomial. I bring down my x and my plus. Half of 2, or 4 is 2. If I square 2, I get 4, and I will add that to both sides. So now this is 5. And then we root both sides. Don't forget there will be a plus and minus in front of that radical. And then I'm going to subtract 2 from each side. Negative 2 plus and minus the root of 5. So back up here, again, earlier through synthetic division, we found one of our zeros was at negative 3, and we just found 2 more of them. Negative 2 plus root 5 is one of them, and negative 2 minus root 5 is the other one. And there we go. Third degree polynomial should have 3 roots. We found one of them was a rational one, and then we found 2 more that were irrational because of that radical 5. All right, example 5. Solve this polynomial set equal to 0. Its fourth power. Ooh, and that constant term is a 24. So when we think about our possible rational roots, leading coefficients of 1, plus and minus 1. So we want all the factors of 24. What divides evenly into 24? Well, 1 does, 2 does, 3 and 4. 5 doesn't work, 6 does, 7 doesn't. 8 does. 9, 10, 11, 12 works. And since we're at the halfway point, there won't be any more until we get to itself 24. So let's see, there's 8 roots there, and there's pluses and minuses of each. So there are 16 possible roots. Should we just begin trial and error? We might just stumble into one of them right off the bat, and that would help, but that would get us down to third degree. We might have to go through that whole mess again. Let's see, could a graph give us any help? If we do this in class, we should have enough time. I'll have you get out and graph this polynomial, and you're going to see it looks something like this. We know by the end behavior it's a fourth power, even, and it's positive x to the fourth. It'll be parabolic shaped opening up, and on our graph we can use the trace feature or the little cursor and get close to this point, and you're going to see that that x value is approximately 2. So there's a clue. 2 is one of our possibilities, and the graph backs it up. So instead of just taking some stabs in the dark, let's try to use synthetic division to pull out a 2. Let's see, we're missing our third power. So our coefficient there is 1, a 0 for the missing third power, and then a -6, a -8, and a 24. And we drop the first term, multiply and add, multiply and add, multiply and add, multiply and add. There it is. Remainder of 0, so we did find a factor. It does say solve this, and it's all equal to 0, so we're looking for our zeros. I'll write them up here in a nice blue color. X equals 2 is one of those zeros. So let's see what we're down to now. We were at a fourth power polynomial. Now it's down to a third power. And then we'll have a plus 2x squared minus 2x minus 12. As far as the factorizations here again go, we got the 24 out of there. So that's gone. Now it's all down to the factors of 12, so I guess we can lose the 8 also. That still leaves quite a few factors. Let's take another look at the graph. Does the graph give us any other type of clue? Look how it touches and bounces off. Remember what that meant if our graph, if we graphically touch and turn around there, that meant we had a root of even multiplicity. We know that x equals 2 is an answer. Well, it might not just show up once in our solution set. It might show up twice because, again, we did not cross the x-axis. We touched and turned around. We could probably pull out another 2. And we bring down our coefficients and drop the 1, multiply and add, multiply and add, multiply and add. So now we have reduced it down again another power. We went from cubed, now it's down to squared, plus 4x plus 6. All right, so back up here to our roots, we do have another one, another positive 2, but since it's a repeater, we wouldn't write it again. But just keep in mind we do have, and yeah, let's just wrap that up. Let's write 2 again, just to be on the safe side. Now, what are we going to do? We could do quadratic or complete the square. Middle term here is even, and that's usually when I go to complete the square. If you want to do quadratic formula, you go right ahead. And our answer should be the same no matter what. Again, bring down the x, bring down the plus. Half of that is 2. Square 2, you get 4. We're going to add 4 to both sides. So now this is going to be a -2 on this side, and that's a binomial squared. And then we square root. So now we have x plus 2 pops out. And we're going to square root over here and at least bring out the negative as an I. And don't forget there's a plus or minus there. Plus or minus I root 2. And let's subtract 2 from each side. X equals -2 plus minus I times the root of 2. Okay, back up here, I just write it out with the plus minus. You know, keep in mind this is two distinct square roots. A negative 2 plus I roots of 2, and a negative 2 minus I times the square root of 2. So fourth power polynomial, and we do have 4 roots. 2, negative 2, or I mean a repeated 2, and then our complex conjugate there. And that, I'm just giving you a little sneak peek here. Oops. Yeah, we already talked about that, what the graph looks like. That's just the picture that comes in the book. This leads us to properties of roots of polynomial equations. If a polynomial equation is degree n, then, even counting multiple roots separately, the equation has n roots. We had a fourth power polynomial. We had 4 roots. A 2 that was a repeater, you know, that multiplicity counts, and then a complex conjugate. So the plus minus gave us 2 more. There were 4 roots to that polynomial. If a plus bi is a root of the polynomial with coefficients b not equal to 0, then the imaginary a minus bi is also a root. In other words, imaginary roots, if they do exist, occur in conjugate pairs. You can't just have one. You're going to have 2 of them because of that plus minus. You know, when we extract these, we got to take a square root of a negative number, and we always have a plus minus, and that's why these complex always come in conjugate pairs. All right, 2 for your personal enjoyment. Number 4 there, find the zeros of that. There's not a whole lot to trial and error on your way through. And let's see, for number 5, also that is solve it, and it is a fourth power. But when you're setting up the possibilities, the leading coefficient is a 1, and this 13 is a prime number. So that makes it a little bit easier to deal with. Pause the video, solve the problems, and then start it back up and see if you got them right. All right, for checkpoint 4, I like to stick with the book's homework setup. Part A is I list the possibilities. The leading coefficient is a 1. Constant is a 2. So our only possible roots are plus and minus 1, plus and minus 2. Let's do a little synthetic division. I always start with positive 1, and our coefficients are 1, 1, negative 5, negative 2. So I drop the leading 1, multiply and add, multiply and add, multiply and add, remainder. No luck. Let's try negative 1 into the same 1, 1, negative 5, negative 2. Drop the leading 1, multiply and add, multiply and add, and didn't work again. 2 and negative 2 are up to bat next. So 2 into the same coefficients. Drop the 1, multiply and add, multiply. Oh, look at that, jackpot. We got a positive 2 is one of our roots. So I'm going to come back up here in blue. Positive 2 is a root, and we have reduced our third power polynomial down to a first power. So now it is x squared plus 3x plus 1. And we want to find the zeros, or the solution, so we'll set it equal to 0. What are the factors of 1 that add up to 3? There's none. So there are no real roots going to be here, or excuse me, rational. We can find some irrational, maybe some complex. The coefficient in front of the x is not even, so here I'd probably lean toward quadratic. A equals 1, b is 3, and c is 1. Let's see if we all remember the quadratic. Negative b plus and minus the square root of 4 times a times c, which in this case, negative b plus or minus b squared, 9, minus 4 times a times c, all divided by 2 times a. So just simplifying under the radical, 4 times 1 is 4, 9 minus that is 5. Radical 5 over 2. Negative 3 plus or minus root 5 over 2. There's our other possibilities. Again, that would be part C, I guess, when we reduced the power and then solved it through alternate means. So one of our zeros was 2, and the other is negative 3 plus root 5 over 2, and also a negative 3 minus the root of 5 over 2. Not imaginary, but they are not rational roots. They are irrational because of that radical. Oops. Okay, that was a third power, so as long as we find 1 and pull it out, we get down to a 1 power lower, which is a quadratic, and we can solve that through complete the square or quadratic formula. This is the fourth power. Leading coefficient is a 1. The good thing here is our constant is a prime number, 13. So our only possible roots are plus and minus 1, plus and minus 13. That's part A. All right, let's try part B. Let's see if we can guess and check ourselves to one of those roots. I guess we'll start with positive 1. Let's see, we got fourth power third squared x, so all powers of x are accounted for. Our coefficients are 1, negative 6, 22, negative 30, and 13. Drop the leading 1, multiply and add, multiply and add, multiply and add. Holy cow. Multiply and add, jackpot. Positive 1 is a root. Let's see here. So now we are down to drop 1 power. Now this will be x cubed minus 5x squared plus 17x minus 13. If you were here in class for this day, we were using the TI-89s earlier. And if you graph, you might see the graph that looks like this, just like we did in the example. So just because we pulled a 1 out of there and it did work doesn't mean there couldn't be another 1 hidden in there. Maybe we have that double multiplicity. So let's try that again, and we'll bring down the 1 and the 5 and the 17 and the negative 13. Drop the 1, multiply and add, multiply and add, and look at that, a double multiplicity. So our zeros, let's start my solution setup here, why not? We have a 1, and we don't have to write it twice, but let's do it again because we want to check and make sure we have all the roots at the end. So we did have that, and we reduced our power down again. We went from cube, now this is squared. X squared minus 4x plus 13 is equal to 0. Get some of this clutter out of the way. The factors of 13 that add up to negative 4. 13's prime. No way we're getting a negative 4 there. So this would be quadratic or complete the square. Again, I see the x term here. The b value is even. So I go to complete the square. Let's see, the 13 will be over here. Now it's negative. I'm going to bring down the x and the minus. Half of 4 is 2, but I'm going to add 4 to both sides. So I'm going to square root. On the left will be an x minus 2. Equals here, I subtract and get a negative 9 and square root that. The square root of 9 is a 3. Negative comes out as an I, and don't forget the plus and minus. So now we add 2 to both sides. 2 plus and minus 3i. So back up to the solution set, comma, 2 plus 3i, and a 2 minus 3i. Let's see, fourth power polynomial, 1, 2, 3, 4 roots. If we count the repeater in there twice, we have a pair of complex conjugates. All right, everything turned out great. Homework, 5 problems. Again, sometimes they take a little bit. That's why there's only 5 of them there, though. And again, make sure you answer all parts, find all roots. If they're asking you to solve it for equal to 0, find all those roots. Enjoy, and I'll see you in class.